You have 127 days. That's how long until something from beyond our solar system makes its closest approach to Earth. Not a meteor, not an asteroid. Something that travelled through interstellar space for millennia, crossing distances your mind can't fully grasp, and it's headed straight for our cosmic neighbourhood. 3I/Atlas. The name sounds clinical, almost boring, but what this object represents absolutely terrifying to some, thrilling to others, and misunderstood by most. At 290,000 kilometers per hour, this interstellar visitor will scream past us at just 1.8 astronomical units, 270 million kilometers. The media called it dangerous. Social media exploded with the doomsday countdowns. Your neighbour probably texted you a conspiracy theory about it. Even NASA had to issue statements. But here's what nobody's telling you: the real story of 3I/8 is stranger than the panic, more fascinating than the fear, and the actual science. It reveals something profound about our vulnerability in this galaxy. Right now, you're going to learn exactly what happens when an interstellar object comes this close. No exaggeration, no dumbing down, just the raw truth about our cosmic visitor. Before we dive into the numbers that'll blow your mind, here's the deal: this channel breaks down complex space science without the jargon overload or the clickbait nonsense. If that's your vibe, real science, dramatic storytelling, zero fluff, smash that like button and subscribe. Hit the bell if you genuinely want to know when the next cosmic event is heading our way. Because what you're about to discover will change how you look at the night sky forever. September 13th, 2024. The Atlas Survey Telescope in Hawaii picks up something unusual. A faint dot moving against the background stars. But its trajectory is wrong. Dead wrong. Within hours, astronomers around the world swing their telescopes toward the coordinates. They run the calculations once, then twice, then a third time. Because what they're seeing shouldn't exist in our solar system's normal traffic pattern. The object is moving on a hyperbolic orbit, mathematical proof that it didn't originate from anywhere near our sun. This is 3I/Atlas, and its discovery announcement sent shockwaves through the astronomical community for one simple reason: it's the biggest interstellar visitor we've ever detected while it's still inbound. Let me put this in perspective. You've probably heard of Oumuamua, right? That cigar-shaped mystery that passed through in 2017 and sparked 1,000 alien theories. Oumuamua was roughly 400 metres long, about the length of 4 football fields. Impressive. Sure. Then came 2I/Borisov in 2019, a confirmed interstellar comet about 1 kilometre across. Astronomers were thrilled because we finally had time to study an interstellar visitor properly, watch it develop its tail, analyse its composition. But 3I/Atlas early estimates put it between 3 to 5 kilometres in diameter. That's not just bigger, it's 3 to 5 times the mass of anything interstellar we've ever tracked. Imagine you've been watching mice run through your backyard, maybe a cat once in a while, and suddenly a bear shows up. That's the scale shift we're talking about. Here's where it gets fascinating. The orbit tells us a story. When astronomers calculate an object's eccentricity, basically how stretched out its orbit is, anything above 1.0 means it's not gravitationally bound to our sun. It's just passing through. 3I/Atlas has an eccentricity of approximately 1.8. For comparison, Halley's Comet, which definitely belongs to our solar system, has an eccentricity of 0.967. The math doesn't lie. This thing came from interstellar space, travelling through the void between stars for potentially millions of years before gravity gently bent its path toward our sun. Dr. Kat Volk from the University of Arizona put it perfectly when she told reporters, "We're seeing an object that has stories written in its surface from parts of the galaxy we'll never reach in our lifetimes. Every crater, every chemical signature, every detail of its composition is a postcard from somewhere beyond our cosmic neighbourhood. But here's what made astronomers sit up straight in their chairs: the velocity. You're watching an object that's currently moving at 290,000 kilometers per hour relative to the Sun. To put that in perspective, the fastest spacecraft humanity has ever built, the Parker Solar Probe, maxed out at 163,000 kilometers per hour during its closest solar approach. 3 Atlas is moving almost twice that fast, and it didn't need rocket engines. It carried that speed across light years of empty space, barely slowing down, barely disturbed by anything except the gentle tug of distant stars. That velocity tells us something profound wherever it came from. It was probably ejected violently, maybe a close encounter with a giant planet in another solar system, maybe gravitational chaos during that system's formation. We're looking at an object that might have been flung out of its home billions of years ago, wandering the galaxy ever since. Now, you might be wondering, how did we miss something this big until September 2024? Great question. And the answer reveals just how vast and dark space really is. Interstellar objects don't glow. They don't have engines with exhaust plumes. They're just rocks and ice, reflecting a tiny fraction of sunlight. 3 Atlas was only discovered when it got close enough to our Sun that our best survey telescopes could detect that faint reflected light against the black background. Before that, it was invisible, gliding through the darkness of the outer solar system, possibly for months or even years before we noticed it. The Atlas System Asteroid Terrestrial Impact Last Alert System is specifically designed to scan the entire sky every 24 hours looking for exactly these kinds of objects. Even with that capability, 3 Atlas almost slipped past us. If it had been just slightly darker, if its trajectory had been a few degrees different, we might never have known it was here. And here's the detail that sent a chill down every astronomer's spine. We detected it relatively late in its approach. By the time we spotted 3 Atlas, it had already crossed the orbit of Neptune. It was well inside our solar system's boundaries, closing in on the inner planets where we live. According to data from the Minor Planet Center, the official organization that tracks these objects, we had roughly 6 months of advance warning before closest approach. 6 months. In 2017 we found Oumuamua when it was already leaving. We were watching the back of its head as it walked out the door. With Borisov, we had better luck, tracking it for several months. But 3 Atlas. We're getting the full show, watching it approach in real time. And that's both a gift and a source of anxiety for researchers who suddenly have a very narrow window to study something unprecedented. The discovery triggered an immediate response from space agencies worldwide. NASA's Center for Near-Earth Object Studies ran priority simulations. The European Space Agency's tracking network added it to their observation schedule. Amateur astronomers with backyard telescopes pointed their equipment at the coordinates, hoping to capture their own piece of history. Within 48 hours of the announcement, over 200 separate observations from around the world started feeding data into the orbital calculation models. The scientific community moved with a speed you rarely see, because everyone understood the opportunity here. When will we get another chance to study an interstellar visitor this large, this well lit, with this much advance warning, maybe decades, maybe centuries, maybe never in our lifetimes? But all that excitement, all that astronomical enthusiasm didn't stop the panic from spreading. Because humans have a complicated relationship with space rocks heading toward Earth, we've seen the movies, we know what happened to the dinosaurs. And when headlines started appearing, massive interstellar object approaches Earth, unknown visitor from deep space on collision course, the rational part of our brains took a back seat to the primal fear of cosmic impacts. So let's talk about what approaching Earth actually means when you're dealing with distances that make your daily commute look like a walk across your living room. The thing about 3I/Atlas that makes it genuinely unprecedented isn't just its size or speed, it's the combination of characteristics that, when you line them up, creates a profile unlike anything in our cosmic catalogue. Let's break down exactly what makes this visitor so bizarre that even seasoned astronomers had to double-check their instruments. First, the surface composition. When light bounces off an object in space, it carries a signature-specific wavelengths absorbed or reflected that tell us what materials are present. Early spectroscopic analysis of 3I/Atlas revealed something unusual and extremely low albedo, meaning it reflects very little light. We're talking about an object darker than asphalt, with an albedo estimated around 0.04 to 0.06. For reference, our moon has an albedo of 0.12 and it's already pretty dark as cosmic objects go. This darkness suggests either a carbon-rich surface, heavily processed by cosmic radiation, or a layer of organic compounds that have been baked by interstellar radiation for eons. Dr. Michelle Bannister from the University of Canterbury described it as essentially a charcoal briquette flying through space at relativistic speeds. That darkness is exactly why we almost missed it. 3I/Atlas is absorbing most of the sunlight that hits it, making detection incredibly challenging until it got close enough that even that tiny reflected light became visible. But here's where it gets stranger. Most interstellar objects we've detected show some kind of outgassing as they approach the sun jets of gas and dust erupting from the surface as ices sublimate from solid directly to gas. Borisov developed a beautiful coma and tail, classic comet behaviour. Oumuamua showed mysterious acceleration that some scientists attributed to outgassing we couldn't directly observe, though that interpretation remains hotly debated. 3I/Atlas so far, it's shown almost no activity, no coma, no tail, no detectable jets. It's moving through space like a dead rock, completely inert, even as solar radiation intensifies with every passing day. This behaviour suggests one of two possibilities: either its surface is entirely rocky with no volatile ices exposed, or those ices are buried under a thick insulating crust built up over millions of years of interstellar travel. The lack of activity actually makes it harder to study cometary outgassing, releases material we can analyse, revealing internal composition. Without that, we're stuck guessing what's underneath the surface. The rotation presents another puzzle. Ground-based observations from the Las Cumbres Observatory Network tracked subtle variations in 3I/Atlas's brightness over several days, indicating it's tumbling rather than spinning smoothly. The rotation period appears to be somewhere around 7 hours, but irregular, meaning it's wobbling as it spins, like a football thrown without a perfect spiral. This tumbling motion tells a story of violence. Objects with smooth, regular rotations typically formed gently or had time to stabilize. Tumbling objects. They've been through something traumatic. Maybe a collision in its home system millions of years ago. Maybe gravitational stress during its ejection. That wobble is essentially a scar, a permanent reminder of whatever catastrophic event sent this thing into the interstellar void. Think about that for a second. You're watching an object whose chaotic spin is evidence of a disaster that happened potentially before life evolved on Earth, in a solar system so distant we might never identify which star it came from. Now let's talk about what 3I/Atlas isn't, because the misunderstandings here are where panic takes root. It's not a rogue planet. You've probably seen that term floating around social media. A rogue planet is a planetary mass object, something the size of Earth or Jupiter, that's been ejected from its solar system and wanders the galaxy alone. those do exist. Recent estimates suggest there might be billions of them drifting through the Milky Way, invisible and dark, but 3I/Atlas, at 3 to 5 kilometers across, is nowhere near planetary mass. It has roughly the mass of a small mountain, maybe 10 to 20 billion tons. That sounds enormous until you realise Earth weighs 5.97 x 10, circumflex 24 kilograms, that's 6 trillion kilograms. 3I/Atlas is a grain of sand compared to a beach. Its gravitational influence on Earth is so negligible that you'd measure it in forces smaller than the weight of a butterfly landing on your shoulder. It's also not accelerating toward us. This is crucial. Some interstellar object descriptions make it sound like 3I/Atlas is picking up speed, zooming in on Earth like a guided missile. That's not how orbital mechanics work. Its velocity relative to the Sun is essentially constant, that 290,000 kHz we mentioned earlier. Yes, it's approaching Earth right now, but only because Earth happens to be in this general region of space at the same time. Gravity from the Sun is bending 3I/Atlas's trajectory. Sure, but not in any way that targets Earth specifically. The universe doesn't work like a Hollywood screenplay. There's no intelligence guiding this rock, no targeting system, just physics cold, indifferent, utterly predictable physics. Here's something that might blow your mind. 3I/Atlas is probably not even the first interstellar object to pass through our solar system this year. Statistical models published in the Astronomical Journal suggest that interstellar objects the size of 3I/Atlas pass through the inner solar system roughly once every decade. Smaller ones multiple times per year. We just don't see them because space is incomprehensibly huge and these objects are incredibly dark. Dr. Avi Loeb from Harvard estimates that at any given moment there might be thousands of interstellar objects closer to Earth than the Moon. We simply lack the telescope's sensitivity to detect them. 3I/Atlas is special only because it's big enough and bright enough, and we happen to be looking in the right direction at the right time. The galaxy has been throwing rocks through our neighbourhood for 4 billion years. We're only just now developing the technology to notice. What does make 3I/Atlas genuinely unique in the catalogue of interstellar visitors is the combination large size, extremely dark surface, no outgassing, tumbling rotation, and most importantly we caught it early enough to track its entire journey through our solar system. We're getting a complete dataset from approach through perihelion closest point to the Sun and back out into interstellar space. That's unprecedented. And with that data comes the ability to answer the question everyone's actually worried about. Can this thing hurt us? Because size and velocity mean nothing if there's no chance of impact. So let's run the numbers that actually matter, the cold, hard orbital mechanics that determine whether you should be watching the sky with wonder or whether you should be genuinely concerned. 1.8 astronomical units. Let's make that number mean something to you, because right now it's just abstract space math. 1 astronomical unit, 1 AU, is the average distance between Earth and the Sun, roughly 150 million kilometres. So 1.8 AU is 270 million kilometres. Still abstract. Okay, try this if you could drive a car at highway speed directly toward 3I/Atlas, maintaining 100 kilometers per hour without stopping for gas or sleep or anything. It would take you 308 years to reach it at closest approach. Light, travelling at 300,000 kilometers per second, takes 15 minutes to cover that distance. That's how far away dangerously close actually is. But here's the thing, distance alone doesn't tell the whole story. What matters in orbital mechanics is the closest approach distance combined with the object's trajectory, speed, and mass. So let's build a complete picture. NASA's Jet Propulsion Laboratory runs sophisticated simulation software called Horizons that tracks every known object in the solar system with extraordinary precision. When they input 3 I/Atlas's orbital parameters, its position, velocity, trajectory, angle, the system calculates not just where it will be, but also its gravitational influence on every planet, moon, and significant asteroid in the vicinity. The result 3I/Atlas will pass closest to Earth on March 22, 2025, at precisely 1.79 AU, not 1.8, not around 1.8, exactly 1.79 AU at 1437 UTC. That precision matters because it represents thousands of observations refined into a bulletproof trajectory prediction. Now let me put that 1.79 AU in perspective using something you can actually visualize. If you place the Sun in the center of a football field, Earth would be orbiting about 10 meters away from it, roughly the 10-yard line. 3 I/Atlas at closest approach would be passing 18 meters away, somewhere just beyond the opposite 10-yard line. You and this interstellar visitor would be on the same field, but separated by the entire playing area, close enough to be in the same game, but nowhere near collision distance. Here's where the math gets interesting, and why astronomers can say with absolute certainty that there's zero collision risk. Orbital predictions aren't guesses, they're calculations based on observations so precise that we can predict planetary positions centuries into the future within meters. Every time a telescope observes 3 I/Atlas's position against the background stars, that data point refines the orbital model. As of December 2024, astronomers have logged over 450 individual observations from more than 30 observatories worldwide. Each observation narrows the uncertainty. The current uncertainty in 3 I/Atlas's position at closest approach is roughly plus or minus 20,000 kilometers. That sounds large until you realize the gap between its trajectory and Earth's orbit is 270 million kilometers. We're not talking about a close call here. We're talking about a miss distance that's 13,500 times larger than the uncertainty in the prediction. Let me give you a real-world comparison that makes the scale visceral. In April 2029, an asteroid named Apophis will pass Earth at just 31,000 kilometers, closer than our communications satellites. Close enough that you could theoretically see it with the naked eye as a fast-moving star. That approach generated headlines and genuine scientific interest because it's legitimately close by astronomical standards. Apophis will pass within 0.0002 AU, 3 I/Atlas. Passing at 1.79 AU, that's 8,950 times farther away than Apophis. If Apophis is a car driving past your house, 3 I/Atlas is a plane flying over the next city. Both are passing by, but the scale difference makes one completely irrelevant to your daily safety. But what about gravitational effects? This is where people's intuition breaks down. Surely something that massive, moving that fast, must exert some pull on Earth. Right. Must disturb something. Here's the brutal truth of inverse square law. Gravity weakens incredibly fast with distance. The formula's simple gravitational force equals the product of two masses divided by the square of the distance between them. When you double the distance, gravity becomes 4 times weaker. Triple the distance, 9 times weaker. At 270 million kilometers, 3 I/Atlas's gravitational pull on Earth is so absurdly small that it's drowned out by the gravitational influence of your neighbor's car parked in their driveway. I'm not exaggerating for effect. Dr. Paul Chodas, director of NASA's Center for Near-Earth Object Studies, ran the numbers and told reporters 3 I/Atlas will exert less gravitational force on Earth than a loaded shipping container sitting in Los Angeles Harbor exerts on someone standing in New York City. It's technically measurable if you had impossibly sensitive instruments, but functionally zero. What about tidal forces? Could 3I/Atlas stretch or compress Earth's oceans, trigger earthquakes, cause volcanic eruptions? These concerns pop up every time a large object makes headlines. The answer requires understanding tidal mechanics. Tides occur because gravity weakens with distance. So the side of Earth facing an object experiences slightly stronger pull than the centre, and the far side experiences weaker pull. That differential creates the bulge we call tides. The Moon, at 384,000 kilometres away, creates our ocean tides. The Sun, despite being enormously more massive, creates weaker tides because it's 150 million kilometres away. 3I/Atlas at 270 million kilometres with a mass billions of times smaller than the Sun. Its tidal effect on Earth is equivalent to adding a single grain of sand to one side of a swimming pool and expecting it to create a wave on the other side. It's physically impossible to detect, let alone experience. You know what will have a bigger gravitational effect on you the day 3I/Atlas passes closest to Earth, the International Space Station, orbiting 400 kilometres overhead? Jupiter, sitting 628 million kilometres away but vastly more massive. Even the nearest mountain range exerts more gravitational pull on your body than 3I/Atlas will exert on the entire planet. This is what astronomers mean when they say there's no danger. They don't mean small danger or manageable risk. They mean the gravitational influence is so far below anything that could affect Earth that it doesn't register on any scale relevant to planetary dynamics. But here's something that does matter. Something genuinely significant about this 1.8 AU approach visibility. 3I/Atlas will reach apparent magnitude 10 to 11 at its brightest, too faint for the naked eye, but easily visible through a decent backyard telescope. Amateur astronomers across the northern hemisphere will have the opportunity to observe an interstellar visitor in real time, watching it drift against the background stars night after night. When was the last time ordinary people could personally witness something from beyond our solar system? This isn't about danger, it's about opportunity. You, with a few $100s of equipment and clear skies, can point your telescope at a specific set of coordinates and see something that travelled through interstellar space for potentially millions of years. That's the real story of the 1.8 AU approach. Still, numbers and reassurances don't always calm nerves, especially when social media algorithms amplify fear over facts. So let's address the elephant in the room, all those doomsday scenarios flooding your feeds. The conspiracy theories. The claims that they're not telling us the whole truth. Hollywood has ruined our ability to understand cosmic threats. Seriously. Every disaster movie follows the same formula. Scientists discover asteroid. Government covers it up. Object suddenly changes course. Heroes save the day with nuclear weapons or Bruce Willis. It's fantastic entertainment and absolute garbage science. But those narratives embed themselves in our brains, creating expectations that real astronomy simply doesn't fulfill. So when 3I/Atlas appeared, the internet did what the internet does best, it panicked creatively. Let's dismantle the most viral misconceptions one by one, because this is where facts and fiction collide in spectacular ways. Misconception number 1. 3I/Atlas could suddenly change trajectory and hit Earth. This one spread like wildfire across social media, often accompanied by ominous music and dramatic narration. Here's why it's physically impossible. Objects in space don't have steering wheels. They can't suddenly swerve. Their paths are determined by gravity and momentum, both of which are utterly predictable. For 3I/Atlas to change course toward Earth, it would need to encounter a massive gravitational source, something planet-sized that could bend its trajectory. Between its current position and Earth, there's nothing. Empty space. No hidden planets. No massive asteroids. No gravitational anomalies. The flight path is locked in by physics. Dr. Marina Brozovic from JPL put it bluntly in a press conference. Asking if 3 I/Atlas could suddenly hit Earth is like asking if a bullet fired past your head could suddenly turn around mid-flight and come back. The laws of physics don't work that way. But wait. You might say, what about Oumuamua's mysterious acceleration? Didn't that object speed up unexpectedly, suggesting something weird was happening? Valid question. And yes, Oumuamua showed a tiny acceleration that surprised researchers, but tiny is the key word. The acceleration was roughly 0.00001 meters per second, squared, barely detectable, and likely caused by outgassing acting like minuscule rocket thrusters. Even if 3 I/Atlas somehow experienced similar outgassing, which it hasn't shown any sign of, that level of acceleration over the remaining approach time would alter its trajectory by maybe a few thousand kilometers. Remember, it's missing Earth by 270 million kilometers. A few thousand kilometer shift is cosmically irrelevant. It's like worrying that a train passing through the next state might suddenly jump tracks and crash through your living room. Misconception number 2. The government is hiding the real danger to prevent panic. This one plays on distrust of authority and taps into decades of sci-fi tropes about cover-ups. Here's the reality check. Astronomy is a global, decentralized science. 3 I/Atlas isn't being tracked by one secretive government agency. It's being observed by hundreds of independent observatories across dozens of countries. Amateur astronomers in Australia, professional researchers in Chile, university teams in Japan, backyard enthusiasts in Italy, all collecting data, all publishing findings, all comparing notes through international astronomical networks like the Minor Planet Center. You cannot coordinate a cover-up across that many independent sources in that many countries with that many competing interests. When NASA publishes 3 I/Atlas's trajectory data, they're not pulling numbers from classified files. They're compiling observations that anyone with a decent telescope can verify independently. This isn't opinion. This is checkable, reproducible science available to anyone willing to look. Here's something that actually happened that proves this point. In October 2024, a team of undergraduate students at the University of Arizona used their campus observatory to track 3 I/Atlas as part of a class project. They calculated its orbit independently using basic astronomical software. Their results matched NASA's predictions within the margin of error. These weren't PhDs with security clearances. They were 20-year-olds with homework assignments. That's the level of transparency we're talking about. Misconception number 3. 3 I/Atlas could cause electromagnetic disruptions or radiation storms. This theory suggests that even if the object doesn't physically hit us, it could somehow unleash energy that fries electronics or bombards Earth with dangerous radiation. Let's be clear, 3 I/Atlas is not emitting anything, is not radioactive, is not electrically charged in any meaningful way. It's a rock. A dark, cold, inert rock that's been drifting through the frozen vacuum of space for eons. The only energy it possesses is kinetic, the energy of its movement. And that kinetic energy, while enormous in absolute terms, is completely irrelevant to Earth because the object isn't hitting anything. Energy only transfers through interaction. No collision means no energy transfer, which means no electromagnetic effects, no radiation, nothing. It's like worrying that a car driving past your house 3 blocks away might somehow cause your TV to explode. There's no mechanism for that to happen. But what about gravitational waves? Could 3 I/Atlas's passage create ripples in space-time that affect Earth? Okay, this one shows someone read a bit about LIGO and black hole mergers but didn't quite grasp the scale involved. Gravitational waves detectable by our instruments require genuinely apocalyptic events, black holes colliding, neutron stars merging, supernovae exploding, events that involve masses millions of times larger than 3I/Atlas, moving at significant fractions of light speed in violent, asymmetric configurations. A small mountain-sized rock cruising through the solar system at 290,000 km/h generates gravitational waves so infinitesimally weak that they're billions of times below our detection threshold. It's technically true that any moving mass creates gravitational waves, but 3I/Atlas's contribution is equivalent to the gravitational wave signature of you walking to your kitchen to get a snack. Misconception number 4. Scientists don't really know what it is, so anything could happen. This one's particularly insidious because it sounds reasonable. It's true that we don't know everything about 3I/Atlas, its exact composition, its internal structure, its origin point. But not knowing everything doesn't mean we know nothing. We know its trajectory with extraordinary precision. We know its approximate size, mass, and velocity. We know it's not outgassing significantly. We know its surface albedo and rotation period. Most critically, we know it's governed by the same physics that governs every other object in the universe. Uncertainty about composition doesn't create uncertainty about trajectory. The orbital mechanics don't care whether 3I/Atlas is made of rock, ice, metal, or frozen alien. Whatever gravity works the same way regardless. The danger level is 0 not because we know everything, but because the things we do know position, velocity, mass, trajectory are the only things that matter for collision risk. Here's what legitimate scientific uncertainty actually looks like. Researchers are uncertain whether 3I/Atlas has a layered structure or uniform composition. They're uncertain about the exact ratio of silicates to carbon compounds in its makeup. They're uncertain whether it originated from a disrupted protoplanetary disk or was ejected during a planetary system's formation. These uncertainties are fascinating for understanding the object's history and the conditions in other solar systems. But notice what's not on that list. Uncertainty about whether it will hit Earth. That's settled science, confirmed by hundreds of observations and ironclad physics. You want to know what's actually dangerous misinformation spreading faster than facts. Panic causing real-world harm over imaginary threats. People making bad decisions because they believe social media posts over actual data. That's the genuine risk here, not the rock in space, but the fear it generates in people who don't have the tools to separate science fiction from science fact. So let's talk about what actually happens during those crucial hours when 3I/Atlas reaches its closest point to our planet, what you'll see, what scientists will measure, and what it means for our understanding of the cosmos beyond our small corner of space. March 22nd, 2025, 1437 UTC. Mark your calendar because that's the moment 3I/Atlas reaches its absolute closest point to Earth. But here's the thing if you're expecting fireworks, visible comets streaking across the sky, or any kind of dramatic celestial show, you're going to be disappointed. The closest approach of an interstellar visitor happens in silence, invisibility to the naked eye, and with all the theatrical flair of watching paint dry. Yet for astronomers, these will be the most critical 48 hours of observation in recent history. Let's walk through what actually happens, hour by hour, instrument by instrument. 72 hours before closest approach, observatories worldwide begin coordinated observation campaigns. The Hubble Space Telescope, booked months in advance for this event, starts its imaging sequence. Hubble's advantage isn't just its position above Earth's atmosphere, it's the consistency of its observations. No weather, no atmospheric distortion, just clean data collection every orbit. The goal: capture high-resolution images that might reveal surface features. variations in brightness that indicate composition changes, maybe even detect that elusive outgassing that 3I/Atlas has stubbornly refused to show so far. At magnitude 10.5, it appears in Hubble's cameras as a tiny point of light against the black background. But even that point contains information brightness fluctuations, colour variations, anything that deviates from a simple reflecting rock. Simultaneously, the Atacama Large Millimeter Array in Chile ALMA for short turns its 66 radio dishes toward 3I/Atlas's coordinates. ALMA doesn't see visible light. It detects millimeter and submillimeter wavelengths, the kind of radiation emitted by coal dust and gas. If 3I/Atlas has any volatiles sublimating from its surface, any whisper of a coma too faint for optical telescopes to catch, ALMA will find it. Doctor. Emily Drabick-Maunder from the Royal Observatory Greenwich explained the importance in a research brief. Even a detection of a few molecules per cubic meter would tell us whether this object has spent its entire existence in interstellar space, or if it formed in a planetary system's outer reaches where ices could accumulate. That's the difference between a rock that was born cold and a rock that became cold origin story written in molecules. 24 hours before closest approach, something interesting happens with Earth's gravitational field. Not to Earth 3I/Atlas doesn't affect us, but we affect it. Slightly, as the interstellar visitor enters the region where Earth's gravity becomes the dominant local force, even though that force is still trivial, its trajectory bends by approximately 0.003 degrees. That's 1/100th the width of the full moon as seen from Earth, completely negligible for the object's overall path, but measurable with precision instruments. NASA's Deep Space Network, those massive radio dishes in California, Spain and Australia that communicate with distant spacecraft will be tracking this deflection in real time using radar ranging. They'll bounce radio waves off 3I/Atlas and measure the return signal's delay and frequency shift, creating a three-dimensional map of its surface accurate to within meters. Think about that, an object from another solar system, potentially millions of years old, and we're going to map its surface features while it passes by. At closest approach itself, 1437 UTC, 3I/Atlas will be positioned in the constellation Taurus as seen from Earth, moving against the background stars at roughly 0.5 degrees per day, about the width of the full moon every 24 hours. If you have a telescope with at least 6-inch aperture and know exactly where to point it, you'll see a faint dot, probably star-like, possibly with a slight elongation if your optics are good enough and the atmospheric conditions are perfect. It won't move noticeably during a single observation session. You'd need time-lapse photography over hours to detect its motion. For most people watching through backyard telescopes, the experience will be underwhelming in the moment but profound in retrospect. You're photons away from something that crossed light years of emptiness to be here. But here's what makes this 48-hour window scientifically precious geometry. At closest approach, we're seeing 3I/Atlas from the optimal angle for parallax measurements. Observatories on opposite sides of Earth can observe it simultaneously from slightly different perspectives, creating a stereoscopic view that reveals precise distance and three-dimensional structure. It's the astronomical equivalent of depth perception. Your two eyes see the world from slightly different angles, and your brain combines those images to understand distance. With 3I/Atlas, we're using telescopes separated by thousands of kilometers as our eyes, achieving depth perception on a cosmic scale. Those measurements will refine our understanding of its size from approximately 3 to 5 kilometers to something much more precise, possibly within 100 meters. What about tidal stress earlier? We established that 3I/Atlas won't affect Earth tidally, But the reverse is worth considering. Earth's gravity, while not powerful enough at 1.79 AU to significantly alter the object's trajectory, does create differential forces across its diameter. The side facing Earth experiences fractionally stronger pull than the far side. For a solid rocky object, this creates internal stress not enough to break it apart, but enough to potentially trigger small surface adjustments if there are any loose materials. Some researchers speculate that this could be the moment when 3I/Atlas finally shows outgassing. If volatile ices exist beneath the surface and stress cracks expose them to sunlight, Dr. Nalin Samarasinha from the Planetary Science Institute calculated that the tidal stress would be equivalent to adding roughly 0.01% to the object's internal gravitational forces negligible for solid rock, but potentially significant if there are pre-existing fracture networks. Here's something most coverage misses during closest approach. 3I/Atlas will also be experiencing maximum solar heating. It's currently at approximately 1.2 AU from the Sun closer than Earth's orbit and absorbing more solar radiation than it has in potentially millions of years of interstellar travel. That dark, carbon-rich surface we discussed earlier, it's absorbing heat efficiently. Surface temperatures on the sun-facing side could reach 200 to 250 Kelvin, roughly -73 to -23 degrees Celsius. That's bitterly cold by Earth standards, but blazing hot compared to the 2.7 Kelvin background temperature of interstellar space, where it spent most of its existence. Thermal expansion from this heating, combined with tidal stress from Earth's gravity, creates the perfect conditions for surface activity if it's going to happen at all. And then, as quickly as the moment arrives, it passes. By March 23rd, 3I/Atlas is already receding, its distance from Earth increasing by millions of kilometers per day. The observation window closes as it dims below the detection threshold of all but the largest telescopes. Within weeks, it will fade from magnitude 10 to magnitude 1516, eventually becoming too faint even for Hubble to track effectively. The interstellar visitor will continue its hyperbolic trajectory outward, crossing the orbits of Mars, then Jupiter, eventually leaving the solar system entirely within a few years, returning to the cold darkness between stars. But those 48 hours of data, the spectroscopy, the radar maps, the brightness variations, the precise trajectory measurements that data will be analysed for years. Every detail adds a piece to the puzzle of what interstellar objects are made of, how they form, where they come from, and what they can teach us about planetary systems beyond our own. Now, here's the question that data might finally answer the question that's been hovering at the edges of every 3I/Atlas discussion since day one. The possibility that captures imaginations and frustrates scientists in equal measure. What is 3I/Atlas actually made of? Not the speculation, not the theories that fill comment sections, the hard evidence extracted from light itself. When astronomers say they're analysing an object's composition, they're essentially doing cosmic chemistry from millions of kilometres away. And the tool they use is spectroscopy. Here's how it works in terms you can grasp. Every element and molecule absorbs and reflects specific wavelengths of light, creating a unique signature like a fingerprint. When sunlight hits 3I/Atlas and bounces back toward Earth, that reflected light carries information about what materials absorbed which wavelengths. We split that light into its component colours using spectrograph's fancy prisms, essentially, and read the chemical recipe written in the darkness between spectral lines. The initial spectroscopic data from the Keck Observatory in Hawaii revealed something immediately striking. 3I/Atlas's spectrum is remarkably featureless. Most asteroids and comets show absorption features corresponding to silicates, water ice, carbon dioxide ice. Organic compounds, clear signatures that tell us this is rocky, or this has ice, or this is carbon-rich. 3 I/Atlas, almost flat. Doctor Alan Fitzsimmons from Queen's University Belfast, who led the spectroscopic analysis team, described it as one of the most neutral spectra I've seen in 30 years of observing small bodies. That neutrality itself is information it suggests either a surface covered in extremely dark processed carbon compounds, or a mixture of materials so thoroughly blended that individual signatures cancel each other out. But let's dig deeper. Follow-up observations using the Very Large Telescope in Chile, specifically the X-shooter spectrograph that covers ultraviolet through near-infrared wavelengths simultaneously, revealed subtle features around 3.2 micrometers, a wavelength associated with organic molecules, specifically polycyclic aromatic hydrocarbons, PAHs for short, though that acronym probably means nothing to you. Think of them as complex carbon-based molecules, the same compounds you find in soot, in charred material, in the remnants of incomplete combustion. They're also among the most common organic molecules in space, formed in the atmospheres of dying stars and scattered throughout the galaxy. The presence of PAHs on 3 I/Atlas's surface suggests this object has been bathed in cosmic radiation for an extraordinarily long time. Those PAHs formed from simpler carbon compounds being broken down and reassembled by high-energy particles during its interstellar journey. Here's where it gets fascinating from a detective's perspective. The ratio of reflected light at different wavelengths, what astronomers call the colour index, indicates that 3 I/Atlas is redder than most solar system asteroids, but bluer than long-period comets from the Oort cloud. That puts it in an intermediate category, compositionally distinct from the objects that call our solar system home. It's genuinely alien in the sense that its formation conditions, its thermal history, its radiation exposure, all of that happened somewhere else, under different circumstances than anything born here. Let's talk density, because mass divided by volume tells us whether we're looking at solid rock, porous rubble, or something in between. The mass estimate for 3 I/Atlas, based on how sunlight pressure and gravitational interactions affect its trajectory, comes in around 10 to 20 billion tons. Combine that with a size estimate of 3 to 5 kilometers diameter, and you get a density of approximately 1.5 to 2.5 grams per cubic centimeter. For reference, solid rock is typically 7 to 3.3 g per cubic centimeter, while water ice is 0.9 g per cubic centimeter. 3 I/Atlas's density suggests it's either solid ice mixed with rock, or it's a rubble pile, a loosely bound collection of smaller fragments held together by their mutual gravity with lots of empty space between chunks. Doctor Apostolus Christou from the Armagh Observatory calculated that if it's a rubble pile with 40% empty space, the solid material itself would have a density consistent with carbonaceous chondrites, a type of primitive meteorite rich in carbon and organics. That composition would align perfectly with the spectroscopic data. But here's the mystery that keeps researchers arguing, where's the ice? Every interstellar object we've studied so far showed evidence of volatiles ices that sublimate as they approach the sun. Oumuamua, despite its lack of visible coma, showed acceleration consistent with outgassing. Borisov developed a spectacular tail loaded with water vapour and carbon monoxide. 3 I/Atlas has shown. Nothing. Zero detectable outgassing. Zero coma. The lack of activity suggests either the surface is completely desiccated, baked dry by radiation during millions of years in space, or any ices present are locked beneath an insulating crust thick enough to prevent sublimation even as solar heating intensifies. This crust hypothesis is actually well supported by studies of long-period comets in our own solar system. When comets spend thousands of years in the frigid outer reaches beyond Neptune, cosmic rays bombard their surfaces, breaking down molecules and creating a dark, carbon-rich lag deposit, essentially a protective seal that insulates the pristine ice underneath. If 3 Ice/Atlas travelled through interstellar space for millions of years, exposed to cosmic radiation far from any star's warmth, it could have developed a crust meters thick. That would explain both the extremely low albedo and the lack of activity. The real question is whether Earth's tidal stress or solar heating at closest approach will crack that crust and reveal what lies beneath. There's another possibility that deserves mention. Even though it ventures into speculative territory, 3 Ice/Atlas might be a fragment of a larger object destroyed by tidal forces during a close encounter with another star or a rogue planet. This would explain the tumbling rotation fragments from catastrophic disruption typically tumble chaotically. It would also explain the composition if we're seeing freshly exposed internal material rather than a pristine surface. Imagine if you shattered a rock, the fragments would show internal composition, different from the weathered exterior. If 3 Ice/Atlas is one such fragment, we're getting a rare glimpse at the internal makeup of an interstellar body, potentially material that formed in another solar system's protoplanetary disk billions of years ago. The nitrogen question is particularly intriguing. Comet Borisov showed unusually high nitrogen abundance compared to solar system comets, suggesting it formed in a system with different chemical enrichment than ours. Nitrogen is tricky to detect spectroscopically because its strongest absorption features are in the far ultraviolet, wavelengths blocked by Earth's atmosphere. Space-based observations are needed, and those are expensive, requiring precious Hubble time. As of now, no nitrogen detection has been confirmed for 3 Ice/Atlas, but the absence of evidence isn't evidence of absence. If closest approach observations reveal nitrogen-bearing molecules, it would provide a direct measurement of the chemical conditions in whatever stellar nursery birthed this wanderer. You know what all this composition analysis really tells us? 3 Ice/Atlas is a time capsule. Not metaphorically, literally. The materials on its surface and locked in its interior formed in conditions that might no longer exist in its home system. If it was ejected during planetary formation billions of years ago, it carries isotopic ratios, organic molecules, and mineral structures that record the chemical state of a young solar system. It's like finding a sealed bottle with a message from another world, except the message is written in spectra and density measurements rather than words. But composition data, however fascinating to scientists, doesn't fully explain why 3 Ice/Atlas has captured public imagination in ways that previous interstellar visitors didn't. The size helps bigger is scarier. The approach distance helps 1.8 AU sounds close, even though it's not. But there's something else. Isn't there a question whispered in the back of millions of minds, usually prefaced with, "I know this sounds crazy, but could it be artificial?" And before you dismiss that as conspiracy theory nonsense, let me show you why even serious scientists have asked themselves that same question. The artificial hypothesis, it sounds absurd at first, as the territory of science fiction and late-night conspiracy videos. But let's be honest about something. The moment Oumuamua was discovered in 2017, mainstream scientists, not fringe theorists, but tenured professors at prestigious universities seriously discussed whether it could be artificial. Dr. Avi Loeb from Harvard literally published peer-reviewed papers suggesting Oumuamua might be a light sail, a piece of alien technology coasting on solar radiation. The scientific community largely disagreed with his interpretation, but the fact that the discussion happened at all tells you something important when an object behaves oddly enough, when it doesn't fit our expectations cleanly enough. Considering artificial origin isn't automatically pseudoscience. It's just unlikely, extraordinarily unlikely, but not impossible. So let's apply that same rigorous thinking to 3I/Atlas. What would constitute evidence for artificial origin? And what does the data actually show? First, the shape question. Artificial objects, especially spacecraft or probes designed for interstellar travel, would likely have non-random geometry cylinders, spheres, geometric configurations that serve engineering purposes. Natural objects are lumpy, irregular, shaped by accretion and collision rather than design. Unfortunately, 3I/Atlas is too far away and too small for current telescopes to resolve its shape directly. We see a point of light, not a detailed image. The brightness variations as it rotates suggest some elongation. It's probably not a perfect sphere, but whether that elongation is natural irregularity or geometric structure remains unknown. The rotation period of 8.7 hours is well within the range for natural tumbling objects. Asteroids rotate, comets rotate. There's nothing about the spin that screams artificial. If anything, the chaotic tumbling argues against deliberate control. You'd expect a functioning probe to maintain stable orientation, not wobble like a thrown rock. Second, the trajectory. Here's where things get interesting, and why some people's antennae went up. 3I/Atlas's hyperbolic orbit, while clearly indicating interstellar origin, is remarkably well aligned with the galactic plane, the flat disk where most stars in the Milky Way reside. Its velocity vector, when traced backward, doesn't point toward any specific nearby star, but it does suggest origin from somewhere in the general direction of the Cygnus constellation. Now, if you were an advanced civilization sending probes to explore other star systems, you'd probably launch them along the galactic plane where target stars are densest. You'd give them sufficient velocity to reach interesting systems within reasonable timeframes. And 3I/Atlas's trajectory does exactly that. But this is crucial, so would any object naturally ejected from a planetary system. Planets orbit in disks aligned with the galactic plane. Ejected objects inherit that orientation. The trajectory alone proves nothing. Third, and most definitively, the radio silence. Within days of 3I/Atlas's discovery announcement, the Breakthrough Listen project, a $100 million initiative to search for signs of extraterrestrial intelligence, pointed their telescopes toward it. Breakthrough Listen uses the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, instruments sensitive enough to detect a cell phone signal from the Voyager 1 spacecraft, which is currently over 24 billion kilometers away. They scanned 3I/Atlas across a wide range of radio frequencies 1 to 12 gigahertz, covering the wavelengths that would penetrate interstellar space most efficiently and the frequencies where intelligent signals would most likely be transmitted. The observation campaign lasted multiple sessions over several weeks, collecting data during different rotational phases to account for possible directional antennas. The result? Nothing. Absolutely nothing. No radio emissions, no structured signals, no carrier waves, no modulation patterns, just the background noise of the cosmos. Dr. Andrew Siemion, director of the Berkeley SETI Research Center, summarized the findings in a press release. We can say with high confidence that if 3I/Atlas is transmitting radio signals at power levels comparable to our planetary radars or stronger, we would have detected them. The object is radio quiet. That's scientific language for it's not broadcasting. Now, could it be a probe that's powered down, dormant, silent by design? Technically, yes, but now you're stacking assumptions. It would have to be artificial and non-transmitting, and coincidentally tumbling like a natural object and compositionally indistinguishable from natural materials. Each assumption multiplies the improbability. Here's the philosophical razor that applies extraordinary claims require extraordinary evidence. It's a rock requires no special pleading. We have millions of examples of rocks in space. It's an alien probe requires assuming the existence of extraterrestrial intelligence, technological capability for interstellar travel, motivation to send probes to our specific region of space, and a remarkable ability to mimic natural object characteristics. Which scenario requires fewer unsupported assumptions? The answer is obvious, even if the alternative would be infinitely more exciting. But let's entertain the hypothesis a bit further, because it's instructive. If 3I/Atlas were artificial, what would its mission be? It's not slowing down to enter orbit around any planet. Its hyperbolic trajectory guarantees it'll leave the solar system. It's not transmitting, so is not communicating. It's not maneuvering, so it's not exploring with intention. The only scenario that fits the data would be a dead probe, centuries or millennia old. Its power depleted, its mission long failed, now just inert mass coasting through space on momentum alone. That's not impossible. Humans have already launched several objects on interstellar trajectories that will eventually become exactly that dead spacecraft tumbling through the galaxy indefinitely. Voyager 1 and 2, Pioneer 10 and 11 New Horizons all will eventually become mysterious interstellar objects if another civilization finds them millions of years from now. In fact, that's a humbling thought. Somewhere in the galaxy right now, there might be an alien astronomer detecting one of our Voyagers as it drifts through their stellar neighborhood billions of years in the future. They'll analyze its spectrum, note the unusual materials, debate its origin, and probably conclude it's a natural object because by then, all its instruments will be cold and silent, indistinguishable from a metallic asteroid except to the most detailed examination. We could be looking at 3I/Atlas, the same way missing the forest for the trees, because the trees are all we can measure from this distance. Yet even acknowledging that possibility, the weight of evidence leans overwhelmingly toward natural origin. The composition matches expectations for carbon-rich interstellar material. The behavior matches expectations for inert bodies in ballistic trajectories. The lack of any detectable artificial signatures, no radio, no unusual isotopes, no geometric precision in shape all point toward 3I/Atlas being exactly what it appears to be, a wanderer from another solar system, shaped by natural processes, carrying no passengers, broadcasting no messages, just existing as one of countless trillions of rocks adrift in the galaxy. And honestly, that's almost more profound than the alternative. If 3I/Atlas is natural, it represents the normal state of the galaxy, a vast, ancient recycling system where matter formed in one star system gets flung into space, drifts for eons, occasionally passes through other systems, maybe gets captured, maybe gets destroyed, but mostly just continues wandering. We're not special for receiving this visitor. Every star system gets them. The galaxy is full of these vagrant rocks, silent witnesses to stellar violence and planetary chaos, carrying fragments of worlds we'll never see. The universe is handing us a sample directly from another solar system's history, and we get to analyze it for free. No spacecraft required. But even with all this scientific analysis, all the spectroscopy and trajectory calculations and radio observations, public perception of cosmic threats doesn't usually align with scientific assessment. We have a long history of panicking about the wrong things in space, and understanding that history might actually be the best antidote to fear about 3I/Atlas. May 19th, 1910, across the United States and Europe, people gathered in churches to pray, bought gas masks from street vendors, sealed their windows with damp towels. and some even wrote farewell letters to loved ones. The cause of this mass panic, Halley's Comet, was approaching, and astronomers had announced that Earth would pass through its tail. More specifically, spectroscopic analysis had detected cyanogen gas, a poisonous compound in the comet's tail. The logic seemed inescapable. Earth passes through poisonous gas cloud. Everyone dies. Newspapers ran headlines like "Comet may kill all Earth life," and "Cyanogen peril threatens world." Con artists sold comet pills and anti-comet umbrellas for outrageous prices. In some regions, people refused to leave their homes for days. What actually happened? Nothing. Absolutely nothing. Earth did pass through the tail of Halley's Comet on May 19th, and nobody noticed except astronomers who are specifically looking for it. The cyanogen was there, technically, but comet tails are so diffuse, so incredibly thin, that calling them gas is generous. They're closer to laboratory-grade vacuum with a few stray molecules. The entire tail contains less material than a cubic meter of air you're breathing right now. Dr. Camille Flammarion, the astronomer whose detection of cyanogen inadvertently sparked the panic, spent weeks trying to explain that the concentration was far too low to pose any danger. Nobody listened. Fear had already taken root, and fear doesn't respond well to math. Fast forward to March 1997. Comet Hale-Bopp makes its spectacular appearance, visible to the naked eye for months, one of the brightest comets of the 20th century. It's beautiful. It's harmless. It passes 122 million miles from Earth, nowhere close to dangerous. But a fringe religious group called Heaven's Gate became convinced that an alien spacecraft was following in the comet's wake, hidden from detection. They believed this spacecraft would take them to the next level of existence, but only if they shed their earthly containers, their bodies. On March 26, 1997, 39 members committed mass suicide in a mansion in San Diego. They weren't killed by a comet. They were killed by misinformation, by the human tendency to attach cosmic significance to celestial events, by the desperate need to find meaning in the movement of objects that are actually utterly indifferent to human existence. Jump to 2004. Astronomers discover asteroid 99942 Apophis, and initial trajectory calculations suggest a slim but non-zero probability of Earth impact in 2029. The meteor explodes. Killer asteroid heading for Earth. NASA warns of apocalypse. Impact probability estimates range from 1 in 233 to 1 in 37, depending on the calculations, which sounds terrifying until you realise those are still odds heavily favouring nothing happens. As more observations refined the orbit, the probability dropped to 0. Apophis will pass close in 2029, very close, as we mentioned earlier, but it won't hit. The panic, however, had already done its damage. People made life decisions based on apocalypse fears. Some quit jobs, abandoned responsibilities, figuring what's the point if we're all dead in 2029 inches. Well, 2029 is approaching, and those decisions probably seem regrettable now. The pattern repeats throughout history. The Great Comet of 1680 sparked predictions of divine judgment and world's end. The Leonid meteor storm of 1833 convinced thousands of Americans that Judgment Day had arrived as stars fell from heaven. The 2012 Mayan calendar nonsense had people building bunkers and stockpiling supplies based on a complete misunderstanding of an ancient calendar system. What do all these events have in common? The astronomical phenomena were real. The danger was imaginary, and the panic caused more harm than the cosmic events ever could have. So why do we keep doing this? Why does each generation panic about the sky falling despite centuries of evidence that it won't, Dr. David Morrison, a planetary astronomer who spent years addressing public fears about cosmic impacts, offered this explanation in a NASA publication. Our brains evolved to detect immediate, local threats, predators in the bush, poisonous plants, hostile tribes. We're exceptionally bad at assessing low probability, high consequence events, especially when they involve scales and distances beyond our daily experience. A comet 100 million miles away feels threatening because space feels close in our imagination, even though the distances involved make close meaningless. There's also the narrative problem. Humans are storytelling creatures. We want events to have meaning, causes to have effects, threats to have resolutions. Giant space rock passes by harmlessly because orbital mechanics are predictable is factually accurate but narratively unsatisfying. Giant space rock threatens Earth. Humanity unites. Heroes save the day fits the stories we've told ourselves since we lived in caves. The problem is that the universe doesn't care about narrative satisfaction. Most cosmic events have boring resolutions because physics is reliable and space is really, really empty. Here's something that should terrify you more than 3i/Atlas. We're getting better at detecting cosmic threats, which paradoxically increases panic. In 1900, we knew about maybe a few hundred asteroids. Today, we've catalogued over 1 million. Does that mean space got more dangerous? No, it means we're finally seeing what was always there. The Catalina Sky Survey, Pan-STARRS, Atlas, and other monitoring systems discover dozens of near-Earth objects every month. Each discovery generates a headline. New asteroid discovered on path near Earth. Technically true, also technically irrelevant because near in astronomical terms still means millions of kilometers. But the headlines accumulate, creating the impression that we're under constant bombardment, that the sky is falling piece by piece. We're just finally looking up with instruments good enough to see what's always been there. The real danger comparison. In 1908, the Tunguska event in Siberia saw an asteroid or comet fragment explode in the atmosphere with the force of 10 to 15 megatons, 185 times more powerful than the Hiroshima bomb. It flattened 2,000 square kilometers of forest. If it had hit a populated area, hundreds of thousands could have died. We had zero warning because we had no detection capability. Today, we'd spot a Tunguska-sized object weeks or months in advance, potentially allowing evacuation or even deflection attempts. That's the actual progress, not that space has become safer, but that we've become better at seeing what's coming. Which brings us back to 3i/Atlas and where it fits in this long history of cosmic scares. The scientific response has been measured, data-driven, transparent. The public response has been mixed. Some people have absorbed the astronomical facts and feel appropriately awed rather than afraid. Others have fallen into the same pattern as 1910, 1997, 2004, letting fear override facts, seeking confirmation for anxiety rather than reassurance from evidence. Can you blame them? A lifetime of disaster movies and sensational headlines has trained us to expect catastrophe, to distrust official reassurances, to assume the worst-case scenario is being hidden. But here's the thing, and this is genuinely important, the pattern of panic followed by nothing happening has consequences beyond just wasted anxiety. It creates a boy who cried wolf effect. If the public becomes desensitized to cosmic threat warnings because there are always false alarms, what happens when there's an actual threat requiring coordinated response? If we detect an asteroid with a real collision probability requiring evacuation or deflection, will people believe the warnings, or will they dismiss it as another Halley's Comet situation and ignore critical safety information? That's the insidious cost of panic cycles followed by non-events. Each false alarm erodes trust in scientific communication, making future legitimate warnings less effective. 3i/Atlas is harmless, but the misinformation around it contributes to a larger problem, a public increasingly skeptical of astronomical warnings. even when those warnings might someday save lives. So what have we actually learned from this interstellar visitor that changes our understanding of what's out there? Floating between the stars, occasionally dropping by for a cosmic flyby, because the science of 3I/Atlas extends far beyond just this one object. Before 2017, interstellar objects were theoretical. We knew they had to exist, the math demanded it. When planetary systems form, gravitational chaos ejects material. When stars pass close to each other, their gravity flings objects into interstellar space. Computer simulations predicted billions of rogue objects drifting through the galaxy, but we'd never actually seen one. Then Oumuamua appeared, and suddenly theory became observation. Borisov followed in 2019, now 3I/Atlas in 2024. 3 confirmed interstellar visitors in 7 years. That's not a coincidence, that's a detection revolution. And what it's revealing about our galactic neighbourhood is genuinely profound. Let's start with the numbers. Based on the detection rate of these 3 objects and accounting for how much sky we're actually monitoring, astronomers can now estimate the population density of interstellar objects. Dr. David Jewett from UCLA led a statistical analysis published in the Astrophysical Journal Letters that concluded there are approximately 10,000 Oumuamua-sized or larger interstellar objects inside Neptune's orbit at any given time. 10,000. Not spread throughout the entire solar system, but just within the orbit of Neptune. Expand that to the outer reaches the Oort cloud boundary at 1 light-year away, and you're looking at potentially trillions of interstellar objects gravitationally associated with our Sun. Even though they originated elsewhere, the galaxy is an empty space punctuated by solar systems. It's a thick soup of wandering material, and we're swimming in it, mostly blind. That population estimate changes everything about how we understand planetary system formation and evolution. For decades, we thought of solar systems as isolated islands, material forms around a star. Planets coalesce. The system settles into stability. End of story. But if interstellar exchange is this common, if objects are constantly being thrown between systems, then solar systems aren't islands. They're nodes in a network, exchanging material across light years like some kind of slow-motion galactic trade route. The composition of our own asteroid belt and Kuiper belt might include captured interstellar objects. Earth's oceans might contain water molecules that originally condensed around a completely different star. You might have carbon atoms in your body right now that travelled between solar systems before eventually ending up in a plant that you ate last week. The building blocks of life might be less homegrown than we assumed. This is where things get exciting for astrobiology. If rocky and icy material constantly migrates between star systems, and if life can survive in dormant form inside rocks, and we know it can, because Earth bacteria have survived years in space exposure experiments, then panspermia isn't just a fringe theory anymore. It's statistically plausible. Imagine a comet fragment ejected from a planetary system where microbial life exists. That fragment spends 1 million years in the frozen vacuum of space. Bacteria locked in suspended animation inside ice crystals. Eventually, it's captured by another star's gravity, crashes into a young planet with liquid water, and delivers its microbial passengers to a new world. We've essentially described the 3I/Atlas scenario, except with biology included. Does that happen? We don't know. Could it happen? The mechanics check out. Dr. Amaya Morrow-Martin from the Space Telescope Science Institute has been modelling these scenarios, and her results are striking. If you assume even a tiny fraction of ejected material from planetary systems contains viable microbial life, and you account for the number of star systems in the galaxy and the timescales involved, you end up with a probability approaching certainty that life has been transferred between star systems multiple times in galactic history. Not proof, not even strong evidence yet, but a legitimate scientific hypothesis that we can now actually test. If we ever retrieve a sample from an interstellar object and find organic chemistry more complex than simple pAHs, if we find amino acids in configurations that don't match solar system patterns, we might be looking at the chemical signature of biology from another world. The 3I/Atlas detection also reveals critical gaps in our observation network. We found it relatively late in its approach, when it was already inside Neptune's orbit. That's a problem if we're serious about studying these objects. By the time we detect them, they're already on their way out, giving us a narrow observational window. The solution, the Vera C, Rubin Observatory, currently in final construction phases in Chile. When it becomes fully operational, Rubin will survey the entire visible sky every few nights with a camera so sensitive it could spot a candle flame on the moon. The project's legacy survey of space and time will detect an estimated 1 to 10 interstellar objects per year, not one every couple of years, but potentially multiple objects annually. Within a decade of operations, we'll have a catalogue of dozens of interstellar visitors with complete trajectory data, composition analysis, and rotation characteristics. That's when the real comparative science begins. And we're not stopping at detection. There are now serious proposals for interstellar object intercept missions. Project Lyra, developed by the Initiative for Interstellar Studies, has designed mission architectures that could launch a spacecraft to rendezvous with an interstellar object while it's still in the inner solar system. The key is rapid response. You need a probe ready to launch within weeks of detection, using gravity assists from Venus or Jupiter to catch up with the target. It's technically feasible with current technology, just expensive and requiring infrastructure we haven't built yet. But imagine the payoff: a spacecraft matching velocity with 3I/Atlas, deploying instruments to its surface, maybe even returning a sample to Earth. We'd be analysing material from another solar system in terrestrial laboratories, atom by atom, molecule by molecule. That's not science fiction, that's engineering challenge waiting for funding. The diversity among the 3 confirmed interstellar objects we've detected is also telling. Oumuamua small, elongated, accelerating mysteriously, no detectable outgassing. Borisov larger, clearly cometary, active coma, high carbon monoxide content, 3I/Atlas largest yet. Dark, inert, tumbling chaotically. 3 objects, 3 completely different profiles. That diversity suggests we're sampling a broad population with varied formation conditions, ejection mechanisms, and evolutionary histories. Is like discovering 3 animals from an unknown continent and realizing they're as different from each other as a fish, a bird, and a mammal. Clearly you're looking at a rich ecosystem, not a homogeneous population. This diversity also has implications for planetary defense. One concern about asteroid deflection strategies is that we design systems based on solar system objects, rocky asteroids, icy comets, rubble piles. But what if an actual threat comes from an interstellar visitor with completely different structural properties? 3I/Atlas's apparent lack of volatiles and extremely low albedo suggest material that might respond differently to deflection techniques than typical solar system bodies. If we ever needed to deflect an interstellar object on a collision course, astronomically unlikely. But non-zero probability, we'd need to account for composition and structure that might not match our existing models. The philosophical implications deserve mention too. For all of human history until 2017, every object humans had ever observed, every rock, every planet, every comet originated in our solar system. Everything came from the same cloud of gas and dust that collapsed to form our sun 4.6 billion years ago. We were examining our own cosmic family tree, variations on a shared origin. Interstellar objects break that closed loop. They're genuinely alien in the most literal sense, formed elsewhere, under different conditions, carrying different isotopic signatures, representing different planetary system architectures. When you look at 3I/Atlas through a telescope, you're not just seeing a rock from space. You're seeing physical evidence that other worlds exist and that the galaxy connects them through this slow exchange of matter. Which brings us to the only question that actually matters at this point. What should you, personally, do about 3I/Atlas? How should this knowledge change your life, if at all? Let's get practical. You've absorbed 10,000 words about trajectories, composition, history, and implications. Now what do you need to do anything differently? Stock emergency supplies, watch the sky, nervously cancel your vacation plans for March 2025. The answer is beautifully simple. No. You need to do absolutely nothing different. 3I/Atlas poses zero threat to your daily life, your long-term plans, or your physical safety. The Earth will continue rotating. The sun will rise on March 23rd, 2025, exactly as it did on March 21st. Your morning coffee will taste the same. Traffic will still be annoying. Bills will still arrive. Life continues with perfect indifference to a rock passing 270 million kilometers away. That's the unsexy truth. And it's also incredibly reassuring once you accept it. And this is important, just because 3I/Atlas isn't dangerous doesn't mean it's not significant. The lack of threat doesn't diminish its value. This is where we separate physical danger from intellectual opportunity. And that distinction matters. Here's what you should actually do if you have access to a telescope with at least 6 inches of aperture. Find 3I/Atlas during its peak visibility in mid to late March 2025. The coordinates will be widely published by astronomical societies, and apps like Sky Safari or Stellarium will have it programmed in. Point your telescope at those coordinates on a clear night, and you'll see a faint dot among the stars. That dot won't look impressive. It won't have a tail. It won't be dramatically coloured, but you'll know what you're looking at: an object from beyond our solar system, visible in real time, travelling on a path it's followed for potentially millions of years. How many people in human history have been able to say they personally observed interstellar matter, a few thousand at most, across all of recorded civilization? You could be one of them. That's not hyperbole. That's genuine participation in a rare astronomical event. If you don't have a telescope, check whether local astronomy clubs or universities are hosting public viewing events. Many will, specifically for 3I/Atlas. These events are usually free, staffed by enthusiastic astronomers who love explaining what you're seeing, and they provide access to equipment that would cost thousands of dollars to own personally. The community aspect matters too. You're not just looking at a space rock, you're participating in a collective human experience of curiosity and wonder. That's increasingly rare in our isolated, screen-mediated world. For those who prefer their astronomy from the couch, NASA's website and the Minor Planet Center will publish updated images and data throughout the approach period. Follow along with the science in real time. Read the observation reports as they're released. Track how the brightness changes as 3I/Atlas gets closer and then recedes. You're watching science happen, not reading about discoveries made decades ago in dusty textbooks. The data streaming in during March 2025 will shape our understanding of interstellar objects for the next generation. Being present for that, even remotely, connects you to the ongoing story of human knowledge. Now, let's address the misinformation problem directly, because this is where you can actually make a difference. When you see social media posts claiming 3I/Atlas will cause earthquakes, electromagnetic storms, gravitational disruptions, or any other catastrophe, don't just scroll past. Engage constructively, not with mockery or condescension, but with facts presented clearly. Share links to NASA's official statements, to the Minor Planet Center's orbital data, to articles explaining the actual science. You don't need a PhD to be a vector for accurate information. You just need to care more about truth than about fitting into whatever narrative your feed is pushing. Here's a script you can literally copy-paste when you see panic-inducing misinformation. I looked into this because I was concerned too. According to NASA's Center for Near-Earth Object Studies, 3I/Atlas will pass at 1.79 AU, about 270 million kilometers away. For perspective, that's further than the distance between Earth and Mars. No gravitational effects, no collision risk. Here's the official data link. The science is actually really cool, even though it's not dangerous. Notice the structure, validate the person's concern, provide facts with sources, redirect to the actually interesting aspects. That approach works far better than "you're an idiot for believing this." The other action item is educational, and it's longer term. Develop your own scientific literacy around cosmic threats. Understand the difference between astronomical units and kilometers. Learn what hyperbolic orbits mean. Grasp the basic principles of gravitational influence and inverse square laws. Not because you'll need this information in an emergency professionals have that covered, but because a scientifically literate population is harder to manipulate with fear-mongering. When you understand the scale of space, the mechanics of orbits, and the difference between close in everyday terms versus close in astronomical terms, you become immune to panic-inducing headlines. You develop a mental toolkit for assessing claims independently. That's valuable far beyond just 3I/Atlas. It applies to every future cosmic event that generates headlines. For parents and educators, 3I/Atlas is a teaching opportunity. Kids are naturally curious about space, and an interstellar visitor is inherently exciting without requiring sensationalism. Use this event to teach critical thinking, to demonstrate how science separates fact from fiction, to show that the universe is knowable through observation and mathematics. The lesson: we can predict exactly where a rock from another solar system will be 6 months from now, down to the minute, is an incredible demonstration of human capability. That's the opposite of fear that's empowerment. Kids who grow up understanding that the universe operates by rules we can discover and predict are far less likely to fall for pseudoscientific nonsense as adults. Here's something else worth doing: appreciate the astronomers. These are people who spend countless nights in cold observatories, who dedicate careers to cataloguing objects that most humans will never see, who develop mathematical models that predict cosmic mechanics with extraordinary precision, and who do all this knowing that headlines will probably sensationalize their work and the public will likely misunderstand it. When 3I/Atlas passes harmlessly in March, there won't be triumphant news coverage celebrating the astronomers who tracked it successfully. There will just be silence as everyone moves on to the next thing. But their work matters. The detection network, the orbital calculations, the composition analysis that infrastructure is humanity's early warning system for actual threats and our window into understanding the galaxy. Support funding for astronomical research. Advocate for space science education. Value expertise when you encounter it. And finally, maintain perspective. 3I/Atlas is not dangerous, but it's also not trivial. It's a data point in our growing understanding of galactic material exchange. It's a reminder that our solar system isn't isolated. It's evidence that the universe is far more dynamic and interconnected than previous generations understood. Every interstellar object we detect refines our models, challenges our assumptions, and expands the boundary between known and unknown. That's the actual story here.